Let's say we have a vector A and an origin point O. In physics, we define the moment of the vector A about O to be a vector whose magnitude is the product of the magnitude of A and the perpendicular distance of O from the direction of A. We can describe the moment of a force as the turning ability of that force. The moment of a force is also known as torque. The moment about the origin of a force F, which passes through a point with position vector r, is given by the vector product r times F, and this vector product has a magnitude of Fr sine theta, where theta is the angle between the position vector and the force vector. To demonstrate the effect of torque on balance, we're going to consider the case of a slender rod with masses attached to it. In this case, we're going to ignore the mass of the rod and we're going to attempt to balance this rod on a knife edge. The 100 kg mass is placed at a distance of 0.8 meters from the knife edge, and the 40 kg mass is placed at 2.5 meters from the knife edge. To find the torque or the turning effect of each of the weights on the rod about the knife edge, we're going to use our expression that torque equals Fr sine theta. In both cases, sine theta equals 1 since the force is perpendicular to the displacement vector. And so for the 100 kg mass, our torque is going to be 100 multiplied by the acceleration due to gravity. And this gives us the weight of the mass, which is the force we need. And we're going to multiply this by 0.8, which is its distance from the knife edge. So the turning effect or the torque of the 100 kg mass is equal to 80 g Newton meters. And for this 40 kg mass, we do the same thing. We multiply the mass by the acceleration due to gravity g, and we multiply that by 2.5, which is the distance of the 40 kg mass from the knife edge. And this gives us 100 g Newton meter. We can interpret this the following way. The 100 kg mass has an anticlockwise turning effect of 80 g Newton meters on the rod, and the 40 kg mass has a clockwise turning effect of 100 g Newton meters on the rod. The 40 kg mass has a higher torque than the 100 kg mass, and so the rod will tend to turn in a clockwise direction. This means that as it is, the rod isn't balanced. If we want to calculate our total torque, we're going to have to subtract the torques from each other because they tend to turn or rotate the rod in opposite directions. So by convention, we take anticlockwise torques as positive. So our total torque is 80 g minus 100 g, which equals minus 20 g Newton meters. To balance the rod, we can change the position of the masses so that the total torque on our rod about the knife edge is equal to 0. Let's say we wanted to keep the 100 kg mass fixed. We would have to change the position of the 40 kg mass to attain balance. Let's call this unknown position of our 40 kg mass A meters. And so our total torque becomes 0.8 times 100 g minus 40 g times A, which gives us 80 g minus 40 g A. For the rod to be balanced, this has to be equal to 0, and so we equate a total torque to 0. Our acceleration due to gravity is constant here, so we can factorize g and take it out of the equation, and we're now left with 80 minus 40a equals 0. Rearranging this equation to find a, we get a as 2 meters. This means that if we keep the 100 kilogram mass fixed, and we shift or change the position of the 40 kilogram mass to 2 meters, our rod is going to be balanced, and the total moment or torque about the knife edge is going to be equal to 0. Alternatively, if we were to keep the 40 kilogram mass fixed, and we called the unknown position of our 100 kilogram mass B, our total moment or torque is going to be equal to 100 GB minus 40 G times 2.5, and we equate this to 0. So we get 100 GB minus 100 G equals 0. Again, since our acceleration due to gravity is constant, we can factorize it and take it out of the equation. And then we're left with 100B minus 100 equals 0. And we can find B to be equal to 1 meter. This means that if we keep the position of the 40 kilogram mass constant, and we change the position of the 100 kilogram mass to 1 meter away from the knife edge, our total moment about the knife edge or torque is going to be equal to 0 and the rod will be balanced. Let's consider a different situation in which the masses and their positions are fixed, and we want to know where to place the knife edge in order to balance the rod. Again, we neglect the mass of the rod and we will assume the length of the rod to be 1 meter. The masses are distributed as shown. We're going to call the position of the knife edge from the 0 mark or origin x bar. And for any mass having a position x from the origin, its distance from the knife edge is going to be equal to x bar minus x. If x is to the left of our edge, we'll get the distance as a positive value. And if x is to the right of our edge, we'll get the distance as negative. This is in line with our convention, since masses to the left give an anticlockwise moment, which we consider to be positive, and masses to the right give a clockwise moment, which we consider to be negative. For our rod with the 3 masses attached, the total moment or torque about the knife edge will therefore be equal to 5g into x bar minus 0.1 plus 7g into x bar minus 0.4 plus 13g into x bar minus 0.9. For us to have balance, the total moment or torque must be equal to 0. There must be no tendency for the rod to turn about the edge. And so we have 5g into x bar minus 0.1 plus 7g into x bar minus 0.4 plus 13g into x bar minus 0.9 equals 0. Again, the acceleration due to gravity is constant since we're under a uniform gravitational field. And so we can factorize g from the left hand side and take it out of the equation. And so we're left with 5 into x bar minus 0.1 plus 7 into x bar minus 0.4 plus 13 into x bar minus 0.9 equals 0. Expanding and rearranging, we're left with x bar into 5 plus 7 plus 13, which is the sum of our masses, equals 15. And so we calculate our x bar to be equal to 15 divided by 25, or 0.6 meters. This point is called the center of gravity of the system, and it means that if we place our edge on the 0.6 mark, or if we try to balance the rod on the 0.6 mark, it would be in balance. We can generalize our solution and say that in a uniform gravitational field, where g is constant, the center of gravity of a system of masses is given as m1x1 plus m2x2 plus m3x3 and so on for as many masses we have, divided by the sum of our masses. And we can write this in shorthand form using our summation notation. We can write x bar equals sigma mi xi divided by sigma mi. In the 3-dimensional case, where we have multiple masses at different points, then the center of gravity will be located at a point with coordinates x bar, y bar, and z bar, where x bar equals sigma mi xi divided by sigma xi, y bar equals sigma mi yi divided by sigma mi, and z bar equals sigma mi zi divided by sigma mi. The center of gravity is the point at which the distribution of weight is equal in all directions. The net torque due to gravity about this point is 0, and the object can be perfectly balanced at this point. The center of mass of an object is the point at which the distribution of mass is equal in all directions. You can call it the average location of the mass distribution. The center of gravity depends on the gravitational field, while the center of mass doesn't. In a uniform gravitational field, the center of mass and the center of gravity of an object are at the same location on the object. We can also find the center of mass of a solid object by visualizing it as an aggregate of many small masses. Take the L block here as an example. To obtain the center of mass of the L block here, we can divide it up into many small masses and then find the coordinates of the center of mass of the L block as x bar equals sigma mi xi divided by sigma mi, y bar equals sigma mi yi divided by sigma mi, and z bar equals sigma mi zi divided by sigma mi, where mi represents a small particle of mass within the L block, and xi, yi, and zi represents the x, y, and z coordinates of that small mass. The purpose of this is just to demonstrate the intuition behind finding the center of mass of a solid object. In practice, we don't actually find the center of mass of a solid object by dividing it into many small masses. We use integration, but that technique is beyond the scope of this video, so I'm just going to wrap things up.